Here, I'll start recording. Okay, so it's recording right now. So I'm just gonna state this for the recording. We went over sig figs real quick. So remember, any number is significant when it's a non-zero, and all zeros that are significant, they have to either be between two significant figures, or for this example here, so 0.060, they have to follow a whole number and a decimal. So in this case, there's two sig figs in this value here, because this 6 is significant, and this 0 is significant because it follows both the 6 and the decimal. This is just for the video because sorry, we forgot to start recording. So there's that. And right now, going for scientific notation, remember that scientific notation, the format is you have a number between 1 and 9.9 times 10 to the power of, let's say, x, of whatever you move the number of spaces in order to get that number of 1 and 9 between 1 and 9.9. So over here, just finished discussing where we found out that this value has 3 sig figs. And since it has 3 sig figs, our scientific notation must have 3 sig figs. So what do I need to do in order to convert this into scientific notation, first of all?
Count the number of spaces from the decimal all the way till you get to one figure in front of the decimal?
Mm-hmm.
Or
I get what you mean. Yeah, so let's do that. So we count the number of spaces from where a decimal would be, right? Exactly. So let's do that. So let's start off to where a decimal would be and start counting our spaces towards this number until we get a number between 1 and 9.9. So we go 1, 2, 3, 4, 5, and then 6. Because here we stopped here because we see that if we just stopped before, we would end up with 60.2, which is not a number between 1 and 9.9. But in this space right here, we do have a number between 1 and 9.9, which is 6.02. So now I have 6.02, and following the scientific format or scientific notation format, it has to be times 10 and to the power of something. Now, what is that something? What number do I put here as my exponent of 10?
A 6.
Mm-hmm. And why do we put 6 here?
It's the number of spaces you move to the right.
Mm-hmm. Or to the left. Yeah, exactly, right? So remember, if you ever, so it's exactly just like that, right? So let's start working with an example that goes backwards, right? So, or I guess goes the other direction. So let's say we have 0.002304. And I want to convert this to scientific notation. So what can I do here? If you guys feel like I'm talking too fast, feel free to interrupt me. I know I can talk fast a little bit. So we have this value here, 0.00234, and I want it in scientific notation. How can I do that?
same way you did it for the last example, except go the opposite direction.
Mm-hmm. Exactly.
So you hit one figure of the decimal.
Yes. So we take this decimal here and we move it over to the right now in order to get a number between 1 and 9.9. So we go 1, 2, and then 3. So I'm stopping here because if I have a decimal here, then it would be 2.304, and that is a number between 1 and 9.9. But if I were to move it one more, it would be 23, and we don't want that. So we would stop here and we would write my numbers. So 2.3. Do I just write 2.3 as it is? I see you guys shaking your heads. So why is that?
No, because you have 4 significant figures, so you must include 4 significant figures in the answer.
Exactly, right? Since this over here has 4 sig figs, we must represent all 4 sig figs in our scientific notation. So we have 2.304 times 10, and to what is it to the power of?
To the negative third.
Mm-hmm. And why am I making it negative this time?
Because the decimal went to the right 3 places this time, instead of to the left.
Yes, perfect. Exactly like that. So remember this, if say you have a problem that gives you, say, to find the to write the original number of, say, 3.6000 times 10 to the power of -5, for example, just remember, if you're moving your if you're going from your original number, right? So your OG number, if you have to move the decimal to the left, it's positive. But if you have to move it to the right, then your exponent is going to be negative. So just remember that. So if that's the case, if I want to convert this to my original number, this 3.6000 times 10 to the power -5, what direction do I need to move this decimal in order to make it my original?
To the left.
Mm-hmm. Okay, yeah, so let's move. Yeah, exactly. We move it to the left, right? Because if our exponent is negative, that means we originally moved it to the right. So to convert it, we got to move it back to the left. So let's do that. Let me change values here. Perfect. So let's do that. So and I know I have to move it to the left, but how many spaces do I move it to the left?
5.
5, because it's times 10 to the power -5, so we got to move back that many number of spaces, right? So let's do that. So it's 1, 2, 3, 4, 5. So our new decimals here, and then we fill in the slot with zeros. So we end up with a final number of 0. Add some 4 zeros, 3, 6. Now, do I include these zeros in here before I move on?
Yes.
So why am I including these last 3 zeros?
For the significant digits.
Exactly. Remember, you got to carry over your significant digits. So after that, we put our 3 zeros afterwards, and we have our original number right here in scientific notation. So remember this of your, your scientific notation with your Sig Figs. It's important to know. Are there any questions regarding this so far? Any concerns? No. Okay. So let's move on into like operations with Sig Figs. So operations with Sig Figs. So let's say we want to add or subtract Sig Figs. So say we have 5.23 plus 5.1. So how many Sig Figs, who can tell me how many Sig Figs would my final answer have?
2 significant figures.
And why is that?
Because of the smaller answer having, or the smaller expo. I don't know how to frame this. 5.1 having less significant figures than 5.23, and you always go with the smallest significant figures.
You're on the right track, but remember, for addition and subtraction, you keep the number. So your final answer must have the same number of decimal spaces as the smallest one in your problem of addition and subtraction. Because over here, we say we have 2 decimal spaces, and over here, we only have 1. So our final answer must have 1 decimal space. So if we were to do that, just quickly add this up, you would then get 10. So if you were to add this up, normally you get 10.33. But since our smallest point is, 1 decimal space, our final answer must have 1 decimal space. So we would round up or down accordingly, and we would keep it as 10.3. Let's see in the chat. And okay. So that's with that, right? So let's work on, say, multiplying and adding, right?
Quick question.
Go ahead.
If the result it was 10.37, I had to round to 4.
Yes. So say your final answer adds up to 10.37, but you needed to be in the first decimal space, then you would round it up to 10.4.
10.4. Okay.
Yes.
Thank you.
You're welcome. So remember to round up and down accordingly, right? So let's say we want to multiply or divide, right? So let's take, for example, let's say we have 6.23 times, let's say, 4.314. So in this one, how many Sig Figs does my final answer need to have?
3.
And why 3?
It's the number with the smallest amount of significant digits.
Right. So if we have the smallest number of significant figures, in this case, this one has 3 and this one has 4, our final answer must have the lowest amount, which is 3, right? So who can tell me what I get if I were to multiply these two numbers with sig figs?
You would get 26.9. Of course, you're rounding up to get 3 significant figures.
Exactly, right? So our final answer with sig figs would be 26.9 because I can see, right? Because before, if you weren't to consider sig figs, you would have ended up with 26.87622, something like that. Since we need to keep 3 sig figs, we need to round up or down accordingly in order to keep those 3 sig figs. In this case, we have right here. So that's a good job right there. And so let's see here. Let's do one more example. Let's do like a mixed operation here where we have both addition, subtraction, and or multiplication, division, right? So let's say over here I have 4.13 minus 2. And then all of it's being divided by, say, 3.16. So what's the first thing I need to do here in this mixed operation?
The subtraction?
Yeah, so let's do the subtraction first. So if I were to do the subtraction first, what would that come out to?
$2.1.
So you leave it as 2.1, right? But remember your rules for sig figs when adding, subtracting, right? Since we're just dealing with like a subtraction problem here, we have to consider which one has the lowest number of decimal spaces. In this case, which one of these two numbers has the lowest number of decimal spaces?
The 2.
Yeah, exactly, right? Because it has none. So technically our final answer for this problem, like this part of the problem right here, would just be 2, because we got to consider the sig figs for that rule. So now we're left with 2 divided by 3.16. And so right now, what would my final answer in sig figs be?
1.
Yeah, so yeah, it'd be just 1, because if you were to just, well, technically you can round it up to 1, but you kind of want to be as precise with the number that you're given. So like, because over here, if you were to work on your calculus, you would get like 0.6329 and et cetera, et cetera, et cetera. So since here, technically you can round it up to 1, but it's not as accurate as to say we would just write it as 0.6. You get what I mean? So remember to work with the numbers that your problem has solved and given you, and keep it to as many sig figs as you can here, for example. Since here, we keep it as 1 because there's only 1 sig fig in this division problem. And here, since we end up with, 0.6329, et cetera, we'll just round it down to 0.6 just to keep our sig figs like that, as well as to be as accurate as possible. So let me rewrite this as 0.6 and like that. Let's see. Does anyone have any questions regarding this so far? Operations, mixed operations. So let's work on one more operation just to get some good practice in. So let's say, for example, I have, let's do this, yeah. Let's say I have 5.55 times 10 to the power 15 times 8.88 times 10 to the power of 18. It's going to be a long one, sorry about this. So divided by, let's say 6.2. And it's going to be, all of this will be added to 5.13. So let's see. So yes, okay, thank you. Yeah, so Victoria, for your question, like how, kind of how Victor said it. So why wouldn't 0.6 be considered 2 sig figs? Well, remember the zeros that come before a decimal, as long as the zero is not in between two significant digits, or does not follow a significant digit and a decimal, it's not significant. In this case, this 0 that we see right here, it's not significant because there's nothing that's coming before it. So there's not a number here in order to make it significant, nor does it follow this 6, because if I were to put a 0 in front of the 6, then there will be two significant digits. In this case, there is not. So that 0 is just there to say, it's like, we could just leave it as a decimal, but that 0 decimal makes it like more clearly seen. So just remember that any zeros that come before any of this is not significant. I hope that answered your question. So let's see here. Yeah, you can technically. So for those of you for those that say you can technically put 0.6 in scientific notation, you technically can if you wanted to. So what would be my, so quickly just go off tangent to answer this question. How can I put 0.6 in scientific notation?
Maybe 6 by 10 to the negative 1.
Let's see, sorry, can you repeat that? It was kind of hard to understand. Let's see. Oh, here. So from what Victoria said in chat, yeah, it would be like that. So we would just move the decimal to the right, and then that would become 6. Well, you would put 6.0 because there's not a 0 following that 6, right? So because we were to put 6.0, that would mean there's two sig figs, but since there's only one, you would just leave the 6. So you would end up with 6 times 10, and since we only moved it one time to the right, to the power of -1. So yeah, this is a really long way to write this like small, easy to write number. But yeah, both of these answers are correct to be either 0.6 or 6 times 10 to the -1. So I hope that helped answer that for you guys. So moving forward onto this mixed operation, right? What's the first thing I can start off with here?
The multiplication.
Yeah, the multiplication. And what can I, so I'm multiplying 5.55 times 10 to the power of 15 times 8.88 times 10 to the power of 18. So what can I, so what comes out of this problem here, this multiplication?
If both of the multiplications has the same number of sig figs. So
Yeah, so since they both have the same number of sig figs, then you just keep that number of sig figs. So they both have 3, then your final answer for this particular problem or section of multiplication will have 3 sig figs. So what is my answer when I multiply these two?
4.92 times 10 to the 34.
No, not quite. So remember, all these are being multiplied together. So let's see. So
Excuse me, what is the number on the right side?
the far
On
right
top of-
side, or oh,
next to that one, the
yeah,
one
oh,
that you.
that was 18. My bad. Yeah, sorry, my
Okay, thank
right
you.
and messily. Yeah. So the number on the left is times 10 to the power of 15, and the one on the right is to the power of 18. So let's see. Oh wait, yeah. Oh yeah, would you say 4 point? Oh, sorry, I was just looking at because I have like the key here and I was looking at the wrong one. So yeah, this is 4.93. My bad. So let's see here. Yeah, so remember it's 4.93, and then I believe, sorry, I can't remember your name, but times 10 to the power of 34. Yes, you are correct. That was on my part. So yeah, so that would come out to 4 point, my bad. Oh, that's not the eraser. There we go. Yeah, so it will come out to 4.93 times 10 to the power of 34. So now that I have that, what can I do next in my mixed operation here?
Divide by 6.2.
So I would divide by 6.2, and what does that give me?
7.9 times 10 to the 33.
So you said 2 sig figs there. Why am I only keeping 2 sig figs there?
because it's a division, so we have to keep the smallest Sig Figs. That is 2.
Yes, exactly. Perfect. So now all I have left is 7.9 times 10 to the power 33 plus, oh, what was my original number? Yeah, 5 point.
I have a question.
Go ahead.
You wouldn't round that up to 8.0?
No, you would not, because you wouldn't, because again, we're trying to keep it at, technically 8.0 is 2 sig figs, but we want to keep it as accurate as possible.
Okay.
So, because back in our calculator, if we were to look at the full number for this value, it will come out to say 7.9490 ... etc., right? Then e to 33. So we want to stay as accurate as possible to just 2 sig figs. So we look at our first 2 sig figs. So here's 7.9, and we look at the following number to see whether we round it up or down. In this case, since it's 4, we can just round it down and just keep it at 7.9. If this were to say be a 5, then we can round this up to 8.0. But
In my calculator, I actually got a 5.
did you?
Yeah, I got 7.95161. I don't know if my calculator's messed up or.
No. Well, in the end, because they're such close numbers, because in our like in the end when we start adding this up, it really shouldn't matter. It should be off by just like a decimal or a place or two, which shouldn't be too bad. So don't, or one place or two, so it shouldn't be that bad. So don't worry about that. As
Okay.
long as you get like really close to that answer, you should be fine. If any of the other people want to correct me, go ahead. So going on to the last part of our operation here, we have 7.9 times 10 to the 33 plus 5.3. So you put this in parentheses to emphasize that this is all part of the same. So who can tell me what would be the answer for here with sig figs?
Is 13 by 10 to the 34?
Can you repeat that again, Victor? It was kind of hard to hear you.
Okay. Is 13 by 10 to the 34?
Here. Sorry, you sound a bit staticky there. Can you try maybe putting it in chat? All right, thank you very much. Let's see, thank you. Let's see. Not quite 13 times 10 to the 34, because let's see. Because, oh, go ahead.
I got the same, 7.9 times 10 to the 33.
Yeah, it would be 7.9 times 10 to the 30, because remember, this is a much larger number, right? Because if we were to multiply, this would come out to say, I don't know, I'm going to say 7.9 bazillion, for example. That's not the actual value for 33 zeros at the end, but yeah. Because what's adding this 5.3 to this, right? So it would just keep it at 7.9 times 10 to the 33. Let's see, someone in chat. Yeah. Remember, we got to keep our sig figs as we go, because remember, which one of these two has the smaller decimal point, since we're technically adding them? Technically the 7.9, right? So we would keep that down here. So pay attention to stuff like these, because you never know when you have like a really large number just being added to something really small. But yeah, this would be your final answer technically for this mixed operation still. Does that make sense? Is there any questions regarding, mixed operations, sig figs, or the scientific notation? All right, I'll take that silence as a no. So let's see in the chat. Perfect. Technically, you still add, because that final number. So if I were to rewrite it, so say it became 7.9 times 10 to the 33. So technically, it's like 7.7 and then 7.9, then like so moves this decimal like 33 places over. And then at the very end, we have like 513, right? Or yeah, 513.13, something like that, right? Because it's such a small number here that we have added on to such a big number that it really doesn't affect it in terms of what we have in scientific notation. but it's still technically added onto it. Yeah, don't worry about it. Perfect. So let's see, kind of a quick roll to the chat. All right. Since there aren't any more questions, we can, let's see, so we can move on to dimensional analysis, and who can take over from me here? Let's see. Kayla, can you go over dimensional analysis with them for me, please?
Yeah, definitely.
Perfect.
Be happy to. Ready. Can y'all see that whiteboard? We're good
Yep,
there?
it's
Okay,
there.
cool. Sweet. All right. So dimensional analysis is just your fancy way of saying that we're about to convert something. And most of what you're going to be converting is grams to moles, to atoms, formula units, moles of another element, right, or part of the compound, right? So let's just go with atoms. When we're doing this, we want to make sure we remember how to calculate molar mass, right? And so when we're calculating molar mass, we want to look at our periodic table, and we get this little drawing up here, right? For an example, let's use hydrogen. If this is our element of hydrogen on the periodic table, we're given quite a bit of information here from each particular element's box, right? So we have our atomic number is 1, but then at the bottom of all of our elemental box, we have another number. And this is known as our molecular weight, right, for each of the elements. And so the unit for this is grams per mole. And that's important to remember as we get into these conversions, what that unit represents. So when we're converting though from grams to mole, it's really helpful to keep in mind that that molecular weight's unit is grams to mole. But so when we're trying to determine molecular mass, if you were just asked to determine the molecular mass of hydrogen, right, it would just be that one single number that was on that element, right? But how do we determine it if we were given a compound, let's say methane? So this has multiple elements in it, right? So how do we go about determining the molecular mass for a compound like that? We'd need to first break it up into its respective parts, right? And so methane has carbon and hydrogen. And to do the molar mass, right, we just look up on our periodic table what the molar mass is for carbon, okay? And so it's going to be that weird decimal number at the bottom of your atomic symbol. And so for carbon, it's 12.01. And then we want to look it up for hydrogen, and it's already on the board. It's 1.008. Okay. And then we also need to determine if there's more than one of each of these elements within the compound, right? And so carbon, if we look back at methane over here, there's only one carbon, right? We only have one of that guy. But we do have 4 of our hydrogen. So in order for our molecular mass of this entire compound to be accurate, we have to multiply by their respective numbers of moles, right? The amount of elements per compound. So we only had 1 carbon, but we have 4 hydrogen. Then our molar mass is calculated by adding that all up together, which should give us something like 16.09, something like that. Take into account significant figures because we just talked about that. So yeah, 16.042 grams of methane, okay? But we just talked about how the unit for molar mass is grams per moles. So if we had 16.042 grams of methane, it's equal to 1 mole of methane. Okay. So that makes sense. We have questions about molar mass. We can do a couple more of those practice ones to calculate that. Can't see anybody's faces. Just gotta assume. All right, so let's try then to calculate the molar mass of, let's do a polyatomic oxoanion that we've been looking at. So that ion's name, does anybody want to venture a guess at it?
Sulfate, right?
Yeah, perfect. Yep, this is sulfate. It has the 4 reference oxygens, giving it that 8 suffix. Okay. But so if we had sulfate here, we want to break it apart. Remember, that's the first step when we're determining our molecular mass, is to break it apart into its different elements, right? And so we have sulfur and we have oxygen. Then we want to determine how many of sulfur we have and how many of oxygen we have. So we only have 1 sulfur, right? And does somebody want to speak up and tell me how many oxygens we have?
We have 4 oxygens.
Perfect, yep. And then we have 4 oxygens. So then from here, what we need to do is multiply the moles, right? Because that 1 represents 1 mole of sulfur, and that 4 represents 4 moles of oxygen. So we want to multiply our moles of sulfur times our atomic weight of sulfur. So everybody look at your periodic table and somebody tell me what the atomic weight of sulfur is.
32.06.
Perfect, 32.06, okay. And then oxygen, so you tell me what the molecular weight of oxygen is.
15.
Say again, I heard a voice, so quiet.
16.
Okay, 16, perfect. And then we just add these up together, and somebody tell me what you ended up getting.
I got 36.092.
36.092 grams per mole of sulfate. And remember, what this means is that 36.092 grams equals 1 mole of sulfate. Okay. It's really helpful to think about it like that as you move into the conversions. Cool. So it sounds like we have a pretty good understanding of molecular mass calculations. So are there any questions about calculating molar mass?
Yes.
Yeah, what's up, Victor?
Well, the answer is 36. I believe that you need to multiply 4 by 16.
Ooh, could you say that again? You're really muffled.
But I believe that you need to multiply 4 by 16.
Oh, he's saying yeah, I was curious about that too. The 16 and the 4, I think, you know, multiply that, no? And then, because I got 96.06 as the
Oh,
weight.
did they not multiply? I didn't double check. I just
Oh,
assumed.
you're good. Yeah, that's fine.
Yeah, thank you. Me too.
Yeah. No, definitely mistakes like that happen. Yeah, so you're gonna, you would multiply 14 times 6.
4 times 6. Or
Yeah.
I heard 14 times 6.
Yeah, sorry, 4 times 16, and then you'd add your 36. Yeah, so that should be a bigger number. That should be closer to 96.16. grams per mole. Thank you. Yeah, we don't want to like confuse y'all without double checking those. Right.
I have a question.
Yeah.
Does the charge affect in any way?
So actually, yeah, it's a really great question. Our charge does not affect our molar mass. Does anybody want to take a guess as to why?
Because the molar mass, it's protons and newtons. And yeah, I think.
Because it's what?
Protons and newtons?
Yeah, so you're exactly right. You hit the nail on the head. Our charges are indicating our valence electrons, right? And valence electrons or electrons don't have enough of a weight, like it's a negligible amount, so they're not calculated into our molar mass.
Okay, thank you.
Yeah, so that's why the charge doesn't factor into how much it weighs. Good question though. So let's try a practice problem where we use that molar mass conversion to go from grams to moles, right? And so we'd have to use molar mass to go from grams to moles or from moles back to grams. Okay, so let's do, had some practice problems. I did. I don't know what I did with them. Alrighty, I'm just a mess. Sorry, guys. If anybody else has one they want to just like volunteer.
Yeah, I can write one up real quick.
Oh, okay, here's one. Never mind, I got it. Okay, let's do, yeah, the moles of chlorine atoms in 83 grams of calcium chloride. Or no, we haven't talked about, no, that'll work. Okay, so we're gonna start, actually let's start by naming or identifying what this compound is. We're told that it's calcium chloride. So does anybody know what that formula would be?
Maybe K3C?
Say it one more time.
K3Cl.
So I heard Cl, which is definitely on point. We need that for chlorine. And then calcium, what's our atomic symbol for calcium?
Ca.
Ca, yeah. Okay, so then now chlorite, that particular name is indicating to us that this is a polyatomic oxoanion, which means it contains oxygen. So we would need to add an oxygen over here by chlorine, but now our ite suffix tells us how many oxygens there are. So does somebody want to take a guess as to how many oxygens are in chlorite?
Would there be 2 oxygens in chlorite?
Yeah, perfect. 2 oxygens in chlorite. And then chlorite has a -1 charge, right? And what's calcium's charge?
2.
+2. So with our crisscross method, right, our +2 is going to go over to chlorite and our -1 is going to go over to calcium. So calcium will stay without a subscript, but chlorite is going to get an extra little 2 over here. Right? So now that we have the name or our formula written out for calcium chlorite, we want to determine the number of moles of chlorine within 83 grams of calcium chloride. So we'll set up our little fence method. I apologize, I have like the worst lag on Zoom when it comes to my little tablet. But yeah, we'll set up our fence method because we know we're going to solve based on our, you know, like canceling out, right? Like when you're multiplying factors in basic like math and algebra, right? You cancel out the numerator and denominator. So it's happening here. So we're going to start with what we were given, which is 83.0 grams of calcium chloride. And it's really important to write out like what you're working with at the moment and what units you're working with, because as you cancel them out, it gets more and more confusing. So I apologize if it gets jumbled. I'm just trying to follow good practices. Okay, sorry. Yeah.
The 83, you, like, it's part of the problem, right? You didn't calculate it.
Yes, yes. The problem was just to determine, let me see, determine determine moles of chlorine in 83 grams of calcium chloride. Ooh, come on. Chloride.
Okay, thank you.
Yeah, no worries. That was a good question. I too would have been like, where did you get that number? Okay, so if we're going from grams to moles, what are we going to need to make this calculation?
Ricardo's number?
Ooh, not quite yet. We'll get there. Right
We
now,
need the molar mass.
yes, perfect. Yep, we need the molar mass of calcium chloride. Okay, so remember we have to take it apart. We have calcium, we have chlorine, and we have oxygen. All right, so how many moles of calcium do we have in the compound?
1.
1, perfect. How many moles of chlorine do we have in the compound?
2.
2, perfect, right. Remember, you know, you're like back to those basic math, you have to distribute outside of the parentheses, right? So you have 2 chlorines. And then how many oxygens do we have?
2.
Right. Remember, we got to distribute that 2 as well to the oxygen. Right. So we'd have to multiply the 2 out here by the 2 on the inside. So that would give us how many oxygens?
4.
Perfect. Okay. And then how much does calcium weigh based on the periodic table?
40.08.
Right. 40.08. How much does chlorine weigh?
35.06.
Ooh. It should be a little higher than that with your, mine normally always says 35.45. And then oxygen weighs how much?
16.
Perfect, right. Okay, and now we add all of this up, and remember, it has to be 2 times 35.45, 4 times 16, okay? Plus the 40.08. So make sure you're following all of those rules.
I got 174.98.
Perfect. That is exactly where you should be. And that's units, grams per mole of calcium chloride. Oops, sorry. Chloride. Okay, so now that we have the molar mass, where is it gonna go in our problem?
On the bottom, so
On the
we can cancel it.
Perfect, yep. Yeah, so we have to put it on the bottom so that we can cancel out those grams. Oh gosh. Okay, so now we can cancel out grams of calcium chloride and grams of calcium chloride. So what goes on top of our molar mass here?
Would it be 1 mole?
Perfect, yep. It would be 1 mole. And that's why we like to think about the unit for our weight, right? It's grams per mole. So that means 174.98 grams of calcium chloride equals 1 mole of calcium chloride. All right, and so now that we have our moles, we're asked to determine the moles specifically of chlorine within this. So we need to cancel out moles of calcium chloride. So where would that go? On the top or the bottom over here?
On the bottom.
On the bottom, perfect. And so we have just 1 mole of that entire compound, and it's gonna go on the bottom over here because we're gonna cancel that out. But now we need to determine the molar ratio of chlorine to that compound, okay? And so we can kind of determine that based on what we did over here with chlorine, right? We had to multiply it by 2. So how many moles of chlorine are there in 1 mole of calcium chloride?
2.
2, yeah. There's 2 moles of chlorine for every 1 mole of calcium chloride. And then from here, we just do our math. And we'll exit out those moles of calcium chloride. We just do our math. So we are multiplying across, and then we divide by what's on the bottom. So 83 times 2 divided by 174.98 will give us our moles of chlorine. So whenever you have an answer, just shout it out. We'll write it down. Double check.
I got 0.9 or 0.94, one of the two.
Yeah. Okay. Well, so if we're taking into account significant figures, right, we would want to determine, the only number we were given was 83.0. So we want to at least have 3 significant figures, right? So what would you end up rounding it to?
949.
I think it should be
0.95.
Yeah, I think it should be 9.5, right? Because that 0 is going to be significant.
Okay, sorry.
Other peer leaders, correct me if I'm wrong. Moles of chlorine. Okay, so we have 0.95 moles of chlorine and 83.0 grams of calcium chloride. Right. Awesome. Takes a little bit, but it's cool to know that you're able to calculate what's going on in a compound. I think it's pretty awesome. All right, do you want to try one that has Avogadro's number in it?
Yes, please.
Okay, so let's do, let's look at the number of molecules. Sorry, it lags so much. In 20.0 grams of CO2. So we're going to go from grams, and then what would be the next thing we need to solve for? If we're going to go all the way to molecules.
Would we need to solve for molar mass?
We'd need molar mass, right? Okay. And then grams divided by our molar mass is going to give us what?
The moles.
The moles, perfect, yep. All right, and then from our moles, we're gonna get our molecules, right? But we're gonna have to use what to get there? Like we use molar mass here to go from grams to moles. What do we need here to go from moles to molecules?
The Avogadro's.
Yeah, perfect, Francisco. We have to use Avogadro's number. All right. So what is Avo's number? What is that constant?
6.022 times 10 to the 23rd?
Yeah, perfect. It's okay, you'll use it so much in Chem 1 that you'll never forget it. All right. And so just so you can like kind of conceptualize what that means, it just means that there are 6.022 times 10 to the 23rd things, atoms, molecules, formula units within 1 mole. Okay, so if you have 1 mole of calcium, it equals 6.022 times 10 to the 23rd molecules. Okay, and this could be any element. It does not have to be calcium. Okay, this could be 1 mole of element X, right, is equal to 6.022 times 10 to the 23rd formula units or molecules, okay, whatever you want to call them. They all mean the same thing. They'll try to trick you up. Don't let it happen to you. Right? So just so we have an understanding of what that means. Okay, but let's go back to what we're solving for. So we're given 20 grams of carbon dioxide, all right? And we know, based on the little plan that we created at the top, that we need to go to moles. So what's the next step in this process?
You need to get the molar mass.
We need to determine the molar mass. Perfect. So our molar mass of carbon dioxide, what are the 2 elements within carbon dioxide?
Carbon and oxygen.
Yep, perfect. Carbon and oxygen. How many moles of carbon do we have in carbon dioxide?
1.
1, awesome. And how much does carbon weigh?
12.011.
Perfect. Okay, and then how many moles of oxygen do we have in carbon dioxide?
2.
2, awesome. And how much does oxygen weigh?
16.
16, awesome. Perfect. So what we need to do is add that up. Make sure you multiply 2 times 16 before you add. And that should give you?
It gave me 44.011.
Perfect. Grams per mole of carbon dioxide. Okay, so if we're given 20 grams of carbon dioxide, where is our molar mass going to go on our fence?
On the bottom.
Bottom, perfect. So 44.011 grams of CO2. And then what's going to go on the top of our molar mass?
1 mole of CO2.
Perfect, yep, 1 mole of CO2. Okay, so now we can cancel out our grams. And we know based on our plan up here, we've got to go to molecules and we're going to use Avogadro's number. So we just have to determine where Avogadro's number is going to go. So, yeah, go for it.
I'm sorry, it's gonna go on the top?
Yeah, it's going to go on the top. And how did you figure that out?
Because we have to cancel out the moles.
Perfect.
So the mole has to be at the bottom, and then the Avogadro's number on the top.
Perfect. Yeah, we know we're trying to get rid of moles, which means we would want to put it on the opposite location. So we'd have Abo's number on the top. And that should give us the amount of molecules that are present in 20.0 grams of CO2. So we would just multiply 20.0 times Abo's number and then divide by your molar mass.
I got 2.74 times 10 to the 23.
That's also what I got. Awesome. All right, and then we just want to make sure that we label it correctly, right? Molecules of CO2. Awesome. Let's do another one similar to that. Or Alana, is it time to move on to another topic, or are we good?
I use in office hours right now, but we have about an hour left, and we're just gonna go over module 2 and then SI prefixes as well. So if you want, you can do like another problem. It's really up to the students. So
Okay.
I don't know what they want.
Yeah. Guys, do y'all want to keep doing conversion problems? Do we want to move on to something else?
Prefixes.
Sorry, can you say that again, Francisco?
Prefix.
Oh, yeah, like
The SI prefixes?
Yes, I'm pretty bad on that.
Kaylee, can you share your screen so I can go ahead and go over that?
Perfect. Yep. I'm going to stop sharing.
Or I don't know if I'm able to.
You should be able to. I'm not, I don't think I'm a host and I was able to.
Oh, snap. Okay, yeah, I was. Sorry, guys. Let me put the whiteboard. Share screen, whiteboard. Okay, cool. Okay, so hold on, let me, okay. So if you guys go to page 40 on your guys' workbook, you have that table with all the SI prefixes, correct? Just so you guys know where they're at. Okay, so we're gonna need to know these, right? So I'm just gonna go ahead and like write this out, right? We have our reference right here, and then we have deci, centi, milli, micro, nano, and pico. Nano and pico. And then going up, we have kilo, mega, giga, and tera. Oh no, I don't know what happened. Mega, giga, and tera. Okay, so what are my conversion factors for each of these, right? So like deci, what's my conversion factor? I also cannot see the chat, so I don't know if you guys are typing it or if you guys want to say it.
1 times 10 to the negative 1?
Yes.
Deci?
Yes. Times 10 to the negative 1, right? And then we just continue down to negative 2, 1 times 10 to the negative 3. And then we go up, we go down by 3s, right? 6, 9, 12. Negative 12, right? And then going upwards, what am I starting with for kilo?
One times 10 to the 3.
Exactly, right? And then we go up by 3s on this end, right? 3, 6, 9, 12. Okay, so a cool mnemonic that you guys can use to like help memorize these is, let me change the color so we can see it. Don't call me your new player. There. And then know my gamer tag. Cool. Yeah, so you can use that mnemonic to help you guys memorize it. I use that. I think it's really helpful. Okay, so now we're just gonna go ahead and start with some practice problems. So if I gave you guys like 900 nanometers, and we're going to convert that to meters. Okay. So we're going to pretty much follow the same like train track thing that Kaylee was using for the moles to grams. Same process, we're just converting between nanometers and meters, right? So we start with 900 nanometers. And we're going to be converting this to meters. So if I know I need to cancel out 900 nanometers to something that's diagonal to it, what do you guys think I'm going to use?
Meter on top and then nanometer on the bottom.
Yes, exactly. Meter on top and nanometer on the bottom. Okay, so the way to like distinguish the difference between these two, like whether I put the conversion factor or 1, is I like to think about it as like, say we were working, well, we're working with, right? So we're working with these guys. So 1 nanometer equals 1 times 10 to the negative 9 meters. That's the weird M. Right? So if I'm following this logic, what do I have right here in this little diagonal to it?
One times 10 to the negative 9.
Actually, for this one, we're going to be using 1 nanometer because we have this 1 nanometer over here, which equals the 1 times 10 to the negative 9 meters on top. Right? Okay, so when I put this in, we know that we multiply our top and our bottom and then divide the two, right? This is just 1, so we can kind of just ignore that. But essentially what we have is 900 times 10 to the negative 9, right? But following scientific notation, we know that this number has to be between 1 and 9. So what do you guys think I need to do to the decimal portion?
Move it over so you get a single digit in front of the decimal.
Yes, exactly. Right, so we're gonna move this over twice to get that 9. So because we moved it over twice, we're also gonna have to change this guy, right? So essentially, it's like you're adding 2 because I moved the decimal over twice. So my final answer will be 9 times 10 to the negative 7 meters. Cool. Okay. We're gonna do some more practice problems. Okay. So let's say we continue with, let's do this. Let's do 11,233 kilograms to micrograms. Okay, so we know we're going to start with 11,233 kilograms. Okay, so what do I have diagonal to those kilograms?
Kilogram? 1 kilogram?
Yes, exactly. 1 kilogram, right? And then 1 kilogram equals what? That goes up here.
It would equal 1 times 10 to the 3 to the 3rd power?
Yes, exactly. Let me draw this. 1 times 10 to the 3. This technically would be grams because it's like we're going back to our base units. Okay, so now that we have that, these two guys pretty much cancel each other out because kilograms and kilograms, they're the same thing, cancel each other out, right? So we know we have our conversion factor in grams. So if I need to cancel this guy out with something diagonal to it, what do you guys think I have there?
1 gram?
1 gram, not quite. So if I know I'm going to micrograms, 1 microgram equals how many grams? If I'm looking at these guys.
1 times 10 to the negative 6 grams.
Yes, exactly. 1 times 10 to the negative 6 grams, right? So now I know that if I have 1 times 10 to the negative 6 grams, this will cancel out with these grams on top, right? So 1 times 10 to the negative 6 grams. So grams and grams cancel. And if I know that this value equals 1 microgram, I have 1 microgram on top, right? And then a cool way to check your work, if you have the right units, is that you cancel everything out, and whatever you're left with last, that's the unit that your answer's in, right? So we canceled out kilograms, kilograms, grams, grams, left with micrograms. Okay, so we can do this, yeah. So once I like multiply my top portion and my bottom portion, we'll do that first. Multiply our top portion times 10 to the 3 over our bottom portion, which is going to be 1 times 10 to the negative 6. What do I need to change to this top guy? What's wrong with this value?
It's not within 1 to, or 1.1 or 1.99.
Yeah, exactly, right? So I need to move my decimal over to get 1.1233, right? So we're gonna go 1, 2, 3, 4, right? So my new value will be 1.1233 times 10 to the what?
10 to the 7th?
Yes, exactly, 10 to the 7th, right? Because we added these 4 decimal points right here, right? And then we're going to divide that by our 1 times 10 to the negative 6. Okay, so essentially what's happening is I'm dividing my exponents, right? So what do I do when I divide exponents? Like, what am I doing to my exponents is my question.
What?
I think I heard it. Did you say subtract them?
I think.
Yes. Okay, well, I'm not sure if that's what you said, but yeah, that's correct. We're going to be subtracting our exponents, right? So 7 subtracted by negative 6, right? Which will technically be what?
13.
13.
Yeah, 13. Remember that when we have, oops, that's a weird thing. Remember that when we have 2 negatives, we're actually adding them, right? Okay, so because we have this new exponent, because we subtracted them, our answer is 1.1233 times 10 to the 13th micrograms. Cool. Okay, I'm gonna go ahead and clear this, right? Okay, we can do a couple more practice problems. So say I give you 40, let's do picograms, and we're gonna go to megagrams. Nope, that is a little wonky. Let me fix that. Megagrams. Okay, so we're gonna start off with our picograms, right? Okay, so what do I have? What do I need to cancel out that picograms?
One picogram?
1 picogram, yes, right? And going based off of our chart, how many grams is in 1 picogram?
One times 10 to the negative 12.
1 times 10 to the negative 12 grams, right? Okay, so pretty much I know I can cancel out my picograms and my picograms. So now I need to cancel out my grams. What can I use to cancel out my grams? If I'm converting to megagrams, what conversion factor is here that I can use?
1 times 10 to the 6 grams.
1 times 10 to the 6 grams, right? And then this will be how many megagrams?
1.
Yes, exactly. 1 megagram. Okay. So when we put 40 times 10 to the negative 12, over 1 times 10 to the 6. Oops, I did not mean to do that. It's 10 to the 6. Okay, so what happens to this 40 and this negative 12? What does it have to go into? If I know this needs to be between 1 and 9, what do I need to move to? Well, how many times do I need to move my decimal?
You need to move your decimal once.
Yes, exactly, right? So then what happens to my exponent?
You would add another decimal place to it, which would become to the negative 11th.
Exactly. The negative 11th, right? And then we have 1 times 10 to the 6th, right? Okay, so then I know that I'm going to be subtracting my exponents here. So I'm going to have 4.0 times 10 to the negative 11th minus 6, right? So what is my final answer once I do this?
Negative 17.
Yes, exactly. 4.0 times 10 to the negative 17th. And this will be megagrams. Cool. We have a couple minutes. Do you guys feel good with this? Do you guys want to go over another practice problem, or do you guys want to move on to module 2?
Move on.
Move on? Cool. So I don't know who wants to go on with module 2. Let me stop sharing.
I can do module 2
Go for it.
already. Give me one sec. Or what about? All right, we'll see. Wait, let me see how it goes. Just the naming. Hold on, give me 1 second, because it didn't do what I wanted. Okay. So module 2 is mainly naming, right? So since hopefully everyone here should be under Dr. Noveron, and he has said all of the students here are under Dr. Noveron. He said that it's going to cover about a good chunk of your exam is going to be naming. And I feel like that's what has been a little bit the most confusing so far. So for starters, before I start, like, just because I want to kind of be guided by you guys. So what part of the module are you guys having most trouble naming? Like acids, ionic bonds, covalent bonds. What are you guys having trouble with?
I'm struggling with acids.
Acids, okay, so we can do some acids. Let's do some acids, okay. So if you guys notice, a lot of acids contain what? Can anybody tell me what a lot of acids contain?
Hydrogen.
A hydrogen, right? So, and it's usually just, so a hydrogen looks like this, the hydrogen ion, right? So that is a key thing to be considered an acid. Usually, almost always, when you see an acid, it's going to have a hydrogen ion combined to it, okay? So there's another thing, though, that you'll see certain types of ions like to make acids. Does anybody know what types of ions like to make acids?
Oxygen?
Yeah, the ones that have oxygens, right? So what were those called, though? The ions that have an oxygen in them?
Oxo ion?
Oxo ions, right? The polyatomic oxo ions, right? So remember that those your polyatomic oxo anions just are, how Kaylee said earlier, it consists of an element. We don't know what element it is, but let's break that word down. So we know it's poly, that means many, right? And we hear the word oxo, so we know that that's at least an oxygen right there. And it's going to say anions. So anions means what? It's an ion, so it's a charged element. But what does the an tell us at the start, the anion part?
And it's a negatively charged ion.
So we know this much, and we know that it's going to have an X amount of oxygens. So once we've broken that word down, like polyatomic oxo anions, you guys for sure know that when you see a polyatomic oxo anion, it's going to look almost like this. You just got to figure out what you're going to put in here, and then next to the charge. So usually, how do I know when, like, what am I going to see in words that's going to be that's going to make that light bulb turn on in my head, that it's going to be like, oh, I know it's going to look like this right here that I've written. So what usually will I see in a compound or in an ion, the name, what will I see at the end?
You'll see the suffix of either H or ite.
Yes. Wait, which one? I heard ite. And then what was the first one?
8.
8. Oh, yes, yes. So yeah, exactly. That's exactly it. So yeah, when I see something that ends with 8 or ite, that's how I know it's a polyatomic oxoanion, okay? So make sure to remember this, 8 or ite. You'll see that once you see that, you'll know that it'll look like this, it'll have this structure. Now it just depends on what I see. So I know I kind of covered the hydrogens first, but let's cover also these because I feel like these are very difficult to memorize, but I want to simplify it as much as I can first. So let's go to those first, and then we'll go.
Can you repeat the explanation for the
what?
For the 8 and 8?
For the 8 and 8. So remember what I wrote down, the polyatomic, or what I said, not wrote down, sorry, polyatomic oxo. Yeah, and if I'm going too fast, let me know, guys. So polyatomic oxoanion. So we broke that. I like to break that word down because I feel like it helps students like realize what's in it. So poly means many, right? So we know that it's 1 or 2 elements, and this could be that one element. I just write the little underline, the little line there, because you know that an element's gonna go there. It could be N, it could be S. You'll see which ones can form those ions. But yeah, so that means poly because it's many. Atomic is just elements, so you know that it's many elements. Oxo is, you know that one of them is going to consist of an oxygen, and then anions, well, you know that just tells you that it's a negative charge, right? So you know this by knowing the ending, which are these. Does that make sense? So it's kind of all connects, they all connect a little bit. So let's say if you see something that ends with 8 or ite, well, you can assume that it's this, a polyatomic oxoanion. And when you assume that it's this, well, you can assume that it'll look like that. Does that make sense? Francisco, was it you that asked? Does that make a little more sense now, or do you still want me to explain myself?
I got it. Thank you.
Okay, you get it? Awesome, awesome. So let's keep going into that. So now we got to form which elements usually form those polyatomic oxoanions. So let's say let's say you guys just see this. They're like name, in your test, it's just like name sulfate. Well, right away, you got to catch this, the 8 part. So let's write it. We know that 8 means polyatomic oxoanion, right? And what does that mean? Well, we know that we're going to have a certain element here, an oxygen here, because it consists of an oxygen. X amount of oxygens we don't know yet, and then we know it's going to have a negative charge. So now you've got at least like maybe 1/4 of the thing done already, right? So now this is where it relies on you guys knowing the names of your elements and your rule of 7 and all of that, which is on page 61 of your workbook, okay? So if you memorize your rule of 7 or just that page 61, well, first, there's no memorization of that page required just to figure out what the element is going to be. We just got to look at the first part. So sulf, what element do you think that is? Sulf.
Sulfur.
Sulfur, right? And what does sulfur look like?
An S.
An S, right? So we know that's going to be SO something. So we got to go back to that page. This is where this little part and this little part does require memorization, okay? So if you look at that page, well, what is the charge of anything under that row, that little box of 4 that you see on page 61? That little box of 4, it tells you that sulfur and some element under it have a certain charge when they form these ions. Can anybody tell me that charge?
2, -2.
2, -2, exactly, right? And now it also, well, we see 8. The 8 tells us one more thing. The 8 also, if you guys memorize these rules, it tells you your amount of oxygens for those certain 4 on page 61. So when those certain 4 elements have an 8 at the end, how many oxygens is that?
4.
4, right? So yeah, it would be SO4 -2. Does that make sense to everyone? All right, so just know that, because think of sulfate like, think of it as like, I'm sorry?
Where did you get the -2?
The -2, well, if you go to page 61 on your workbook, it's just a rule you got to memorize. if you see that there's a little box of 4 in page 61, there's a little box of 4 elements. So it should be P, and then to the right it's S. Then below it's, I think it's AS, or correct me if I'm wrong. I think it's AS, or it should be another element. Let me look at my periodic table real quick. SE, I'm sorry. So it should be PS, and then below that SE, and then to the left of that AS. So do you see which elements I'm talking about?
Yes.
So those elements have a certain charge and a certain number of oxygens that they need. So if you look at that page 61, it'll tell you that, and it'll also tell you the charge. So S, if you see it, S and SE need a charge of -2, right? When they form a sulfate ion, or like a polyatomic oxide ion.
Okay, thanks.
Yeah, no problem. So now, real quick, so you guys realize that the charges don't really change. So let's look at sulfite now. So ite, let's look at that. Well, we know that it's gonna be, so we already know what S is. So S, and then sulfite, we know that it's gonna have oxygens. Let's say we don't know how many yet, okay? So, and it's gonna have a charge. Does the charge change with the naming?
No.
No, right? So just always know that when sulfur forms like a bond, well, not a, yeah, a bond with the oxygen to form an ion, the ion will always have the same charge as what it's been told in your book. Just the amount of oxygen changes. So remember, sulfate was what? SO4 -2, right? So can we call this sulfate still? Can we call this sulfate? Well, no, because now we're being told that it's called, I mean, I'm sorry, can we say that this is SO4? Can we say that sulfite is SO4?
No.
No, right? Because we already said that this is SO4, that sulfate is SO4. So the ite means that it's telling us something. So it's telling us that ite, if you guys look at your book, ite means that you've lost an oxygen. That's what ite means, basically, in a sense. You've lost just one. So if we lost just one, how many oxygens are we going to have?
3.
3. Exactly, okay? So that would be sulfite. So now there's one more thing. So now let's say you're being told that sulfite has lost one more oxygen. So now you can't call, so that would be SO2, right? So someone told you that sulfite lost an oxygen. What do I call that? Well, you can't call it sulfate. You can't call it sulfite. Exactly, not necessarily. You gotta tell them, whoever that student or whoever you're explaining it to, you've got to tell them that you've lost one more oxygen. So how would we say that? How do we tell someone that it's lost one more?
With the prefix hypo?
With the prefix hypo, exactly, right? So remember, sulfite, we can keep the sulfite because in a sense we have lost one from the original. So think of 8. So remember, 8 was 4 oxygens, 4 O's, 4 oxygens. Well, ite tells you that it goes to 3. So it lost 1, so -1. And then hypo tells you that it's lost 1 more, so you go to 2 oxygens, 2 O's. That's supposed to be an S right here. Sorry about that. Didn't want to confuse you. So yeah, O's. So now this tells us that it's lost. So this tells us that it lost 1 from the original 8, and this tells us that it's lost another 1 from the original 8. So does that make sense? So 2 oxygens lost, you would get hyposulfite. So does that explanation make a little bit more sense? Did it confuse, or how do you guys feel on
it? Sorry. Sorry.
Alrighty, so let me give you guys another problem. Let's say I told you guys, let's write hypophosphite.
Can I ask something?
Yes, what's up?
The original for all of the elements, it's 4, or it depends?
Oh, the oxygens? Well, it just, so if you look at page 61, you're saying like that, so only those certain 4 elements need 4 to be called 8. Is that what you were asking, or?
Okay.
Yeah, so let's look at the rule of 7 real quick, just to make sure.
Andrew, can I interrupt real quick?
What's up, Jimena?
Okay, so guys, I sent a picture through the chat. It says rule 7. That's basically what we're talking about. There you can see the charges and the reference numbers. So the reference number of oxygen only applies to those elements. And the ones with a 4 means that they need 4 oxygens in order to be called 8. And the ones on green are only need 3 oxygens. Does that make sense?
I was gonna say yes, like if I was like the student.
Yeah, but I saw someone nodding, so yeah.
Okay, so yeah, basically, okay, so this is a rule of 7. The rule of 7 just means the top. I like to think of this as the rule of 7 just means these elements. You can think, I like to think of it the rule of 7 because if you count them, it's 1, 2, 3, and then 4, 5. Wait, everybody can see my mouse, right? Or can you guys see my mouse? Okay, so yeah, it's B is 1, 2, 3, and then 4, 5, 6, 7, right? You can think of that. That's why it's called the rule of 7, or you can also see it as like it forms a little 7 up here. Like if you notice that, that's the rule of 7. These are separate though. So remember the rule of 7, they need 3 oxygens to be called 8 to get the suffix 8. Okay. These 4, well, you can think of that also like this little box of 4 needs 4 oxygens to get called an 8. So I like to call these, you see them in your book called the reference. Yeah, the reference. So these are the reference. So think of 8 as your base model, like your base, the one that you guide yourself on, you know what I mean? So yeah. So remember, it doesn't matter really how much oxygens they have, just remember the rules are the same. So if you get ite, it just lost 1 oxygen. So you just got to be careful as to what elements you're looking at. So like if one of these 4 elements is called an ite, just know that it lost 1 from the 4 original, you know, so it'd be 3. And then this, well, it doesn't matter if you see like nitrite. If you see nitrite, well, you know that nitrate is 3 because it's part of this rule. And if you see nitrite, we'll just think nitrite just means 1 oxygen less. So minus 1 oxygen, that's 2 oxygen. So you know that nitrite would be NO2. And then with the charge of it, that was horribly written, but yeah. But does that make sense a little more? Or I forgot who asked it, but did that make a little bit more sense? Yes? Okay, cool. So let's keep going. So let me give you guys, I want to see if you guys on your own can name this. So hopefully, yeah, I'll give you guys a minute or like 30 seconds. Because yeah, this honestly, in your test, you should get to a point where you can look at these and within 5 seconds, you already know what that's called. So anybody within the next 20, 30 seconds, can you guys tell me what this would be?
I think I got it like PO2 minus the 2 on the top, minus 2 on the top.
Oh, minus 2 on the top, okay.
Yeah.
And then?
And then 2 on the bottom, yeah.
So like that?
I think so.
Okay, does anybody agree or disagree with this answer?
Isn't it -3 on the top?
Exactly, yeah, it would be -3 because just remember where the P is located at and remember what charge is under those elements, okay? Under the P and the AS. Okay, so, and what about the oxygens? Does anybody disagree with the amount of oxygens or agree? No, right? That would be correct. So, I'm sorry, what's up?
From where we get the -3?
The -3, so the charges, just remember the charges, that's something you've got to memorize. And luckily we have on page 61 of your workbook, we have the little chart that tells you the charges, okay? So yeah, honestly, there's no explanation like that I can give you, like the reasoning, like it's just, that's the charges that are given to you. Like you learn later on why it's 3, but it's more like it's got to do with electrons and all that. And you guys will learn it like till the end of the semester. So, but as of right now, just this is what they are. You know what I mean? And you look at page 61. Okay. So I want to avoid something that some students have gotten confused with. So in your book, I keep saying it's page 61. Is it page 61? Because anybody can correct me if it's not page 61.
Yeah, it's 61.
Okay, 61. All right. So you'll see that page 61 gives it to you like this, right? They tell you this, this, and then they cross out oxygen, they cross out fluorine, and then they tell you that -1 is all of this, like, and below. So all of the ones in below are -1, right? So real quick, don't get this confused with what the charges are of the elements separately. So what I want to say is, like, what's the charge of nitrogen? Without looking at this graph. So don't think of, because they're two different things. Because if you guys have seen, you guys probably will see that the charge of nitrogen, you've seen this too, right? I think on some other separate graphs. Yes, no, or no?
Would it be plus or minus 4 for the charge of nitrogen?
That'd be carbon. That'd be carbon. So remember, it's because this is the charge of nitrogen when it's forming compounds, okay? This is the charge of nitrogen when you're forming polyatomic oxo anions, okay? So yeah, I want to avoid that confusion because people think that sometimes they think that the charge of nitrogen on its own is -3. What this is saying, what this little -1 is saying is that when you form it with 3 oxygens, it'll be -1. Okay? Because yeah, I noticed that if you guys look at like some other, if you guys were to look up online, like what's the charge of carbon, you would see ±4. But here you're being told that it's -2. Well, yes, it is -2 only when you're forming it with an oxygen ion, okay? Does everybody know what I mean by this? I want to avoid that confusion. I don't know if that might have confused you a little more, but hopefully it didn't. But just know that, yeah, these things, don't think of that page 61 as them telling you the charges of the element. It's not telling you the charges of the element. It's just telling you the charge that it'll make with the oxygen, okay? All right, so I want to avoid that.
So in that rule of 7, those charges, like the ones in the middle, the P, the S,
Okay.
SE, those are -3, right? All of them.
Just some of them. So here you'll see that it's split up like this, right? And then it's what,
Yeah.
AS and SE. So
Yeah.
these are -2. And what this means is that all of these, so let me color code it. So let me erase this and erase this. Okay, so let me do it in different colors. So this is P. Oh my God. Okay. Wait, hold on. I don't know why it's not changing colors. Okay. I'm having a little. Okay, there you go. Okay. P and then. Okay, I'm like. Okay. Hold on. P, then AS, then S, then SE. And I should have done it in different colors. Okay. So S and then SE. So these are -2, and then these are -3. Okay.
All right. Thank
Yeah, that's what they're telling you in that page. Okay.
you. Okay, thank
I
you.
have another trick for you guys. On the rule of 7, you basically just have to count from left to right, like -3, -2, -1.
Yep, exactly. Just know where you got to start. So if you start on nitrogen, just remember, yeah, it's like Jimena said, -1, -2, -3. And yeah, and then chlorine and all your halogens are just -1 overall. And you can think of it also like this, like it's -1 here, and then just ignore the top ones, and then it's -1, -2, -3, you know? So just make sure where to start, okay? So yeah, I just wanted to avoid that confusion with the charges. So now, let's see what else we can name. So can anybody name, okay, so name this one. And then can somebody name the bottom one? So real quick question. Between these two, which one do you guys think I can buy somewhere, or I can somehow obtain physically?
Between the two, it'd be NO2.
NO2, right? Why did you choose the NO2? Yeah, Jose, I saw you're correct. So Sebastian or Jose, either one, if you can turn on your mics. Why would you say NO2?
So NO2 because it's not an ion, it's a Yeah, it's just because it's not an ion.
And what is this? So what is the NO2?
Nitrous oxide.
Yeah, yeah, it would be nitrous oxide or yeah, nitrogen dioxide. But you're correct with the naming, but what is it though? Why is it something that I can physically see or find or buy or breathe even? I don't know what it
It's
would be.
used for to give boost to cars or to other motor vehicles.
Exactly, but what I'm saying is it's a compound. It's a compound, something that's already neutrally charged, so it's formed something physical. You know what I mean? So
Yeah.
exactly what you said, it could be used in cars. That's because you can see it. You can use this. This is an ion, which means it needs to be bonded with something to form a compound, which is something that you can see. So think about it as this being like super tiny, like atomic tiny. So that's why you couldn't find this in the store. That's why this is an ion and this is a compound. So that's the difference between the two, okay? And now you said it could be called, yeah, I've seen that it's called nitrous oxide, but just for the sake of the naming that you guys are using, let's call it nitrogen dioxide because that is also a correct name for it, okay? But yeah, nitrogen dioxide, and so this is called the what ion, Len?
That is nitrite?
Nitrite, exactly. Nitrite will, hopefully everybody already knows how he got nitrite from. If not, let me know though, if you guys did not understand. Okay, all right, so now let's get into acids. Okay, so I feel like Jimena and Diana, do you guys want to take over acids?
Can you back again to the last slide? A little
Which
bit,
one?
that one. Okay, thank you. I just want to check something. Thank you.
Yeah, no problem. So yeah, we can go. So Jimena, do you guys want to go into acids, and Diana, or?
You can go ahead. Or Diana, do you want to go ahead?
I don't know, however you guys want. It's just like exactly the same. You're just adding like hydrogen. So
Okay, so let's keep going into it then, I guess. So acids. So Diana, let's make let's get a, so remember how Sebastian said earlier, we're gonna get a hydrogen and a sulfate ion, right? So sulfate was SO4, -2. So when I'm mixing these, do I really need to look at this 4 right now? Why not? So Diana or Jimena, can you guys tell like the students why I don't need to look at this 4? What do they need to consider this thing as so they won't look at the 4?
Okay, so you need to consider it as a whole.
Yeah,
So
consider it as a
imagine
whole.
like if it were in between a parenthesis. So don't pay attention to that right now.
So yeah, think of this as one thing. So think of this as exactly the same as this. So like yeah, because just think of sulfate, you need 4 oxygens to have sulfate. So you can't change the number of this oxygen, the number of these oxygens. Okay, so when you combine them, well, you can do the crisscross method like you've been doing before, but if you've been in my workshop, you know that I don't want you guys to learn it just like this because it can cause a lot of, it could cause some confusions maybe, because I've had students where if something has a charge of 2 and then it has a -2, they usually, so this, let's say this is X element and this is Y element, like just imagine these are elements. People, when they combine them, they can do this. Would that be correct? No, right? Because remember your charges got to cancel out and technically they're not canceling out this way by doing it like that, okay? So just think of it mathematically, okay? So let's say you want this to equal to 0, right? So you know that you want -2 and you want +1 to equal to 0. Well, what can you, I was like, who's writing? What can you do mathematically just to get them equal to 0? What's the easiest, simplest thing you can do?
Add 1 and then subtract it by 2.
Add 1, yeah, add 1, right? Or so you're adding another hydrogen, correct? So by saying that, you're saying add another 1. So think of this more like ratios. So in ratios, you don't add or subtract, you're technically multiplying. So when you're, so yeah, you added 1, but preferably just say multiply, you doubled it, right? So we doubled our amount of hydrogens. So now that becomes +2, +2 minus 2, that now it gives us 0, okay? So you said that we're gonna need 2 hydrogens. So instead of writing 2 hydrogens out, what's a better way that I can write, that I can tell you guys that I have 2 hydrogens? What can I write?
Hydrogen subscript 2.
Subscript 2, and remember, subscripts are your small tiny little letters at the bottom. So now I've combined it with the sulfates. So how many sulfates did we need? Well, one sulfate has a charge of 2. Did we change the amount of the -2? No, we didn't multiply by anything, so we only used one sulfate. So it stays as 1. Think of it as also being like this, but remember, when you have an amount of 1, you don't need parentheses. So you can erase this, and you can just have it like that, H2SO4. And now, do you guys notice how it doesn't have a charge anymore? It doesn't have a charge. So this is a compound now, right? So this is something that I can find in the store. I can find sulfuric acid in the store. I don't know why I would be looking for it, but I can if I wanted to. So yeah, and this would be your acid. Now, I think I already said the name, but hopefully I said it too fast that you guys didn't even hear. But what would it be called?
Sulfuric acid?
Sulfuric, exactly, right? So tell me how you got that, though.
So with the H, we know it makes an acid, and because of the oxygen atom, it would take out the hydro as a prefix, and then whenever it's an acid, it depends because sometimes it can be ic or us.
Yes, exactly. Okay, so in simpler terms, just if you separate this back into the ion, what do we call it?
Sulfate.
So yeah, what you said was exactly right. So let's keep on. So this was a sulfate, which was your polyatomic ions, right? Your polyatomic oxo anions. So this is just a rule that you have to remember. If it ends in 8, and it becomes an acid, what do we call it at the end? Well, you called it sulfuric, and I said you were correct. So just remember that. When something ends in 8, so like your sulfate, nitrate, phosphate, all of those, and you make it into an acid, well, the H just lets you know that it's an acid, and the ic just lets you know that before it was an 8, before you combined the hydrogen and the polyatomic ion. Does that make sense for everyone? So you said 8 equals ic. So what if I want to tell you that I made an acid with sulfite, though? I mean, yeah, with sulfite. So could I still call it sulfuric acid? No, right? I gotta call it.
I think it'll be sulfurous or
sulfurous acid. That's exactly right. So let's write it out anyways, because I feel like I'm a visual learner, and hopefully you guys are too. So let's write it out anyways. So I told you that I wanted to make an acid with sulfite. So what does sulfite look like? Again, can anybody tell me?
SO3 -2.
SO3 -2, right? So 3, yeah, that's exactly correct. And remember, the acid tells me that I'm going to have what other element combined?
Hydrogen.
Hydrogen, right? And hydrogen just looks like this. Okay, so, well, let's combine it. And like I said, think of this as parentheses. So now you can do your crisscross method. Like once you know what you're doing, like the whole math aspect of it, that's what I want you guys to know for sure. After you guys know that, then yeah, just trust doing the crisscross method. So this would become H2SO3. So yeah, and this was sulfite. So now you made it into an acid, so you know that it's going to be something acid. So just remember 8 equaled ic, so you can't call it sulfuric because it wasn't sulfuric. So how we said it was ite would equal OUS. And this is just a rule that you also have to memorize. So it'd be sulfurous acid. Okay, so I don't know what little mnemonic devices you guys like for these. I always just thought to myself, if you say it's all right with us, so it's all right with us or us, you know? And then I just memorized that one because then I could be like, oh, the other one just ate and ick, you know? Because I don't have a mnemonic device for the top one. So, but I just thought if I memorize the bottom one, well, the other option's got to be the other one, you know? So.
On the top one, I ate something icky.
Oh, that's good. Yeah, I ate something icky. Okay, yeah, you could do that one too. I didn't think of that one. Oh, that's good. So yeah, that was naming. So how do you guys feel? Because we have about 8 minutes. So do you guys have any other examples that you'd like to go over, or any? Because we didn't really go over ionic or covalent bonding. What about that? What do you guys feel on that?
Can you just explain a little bit about the covalence and
Yeah, for sure. So covalent is what? What does that mean? Covalent bond. Anybody describe anything about it to me?
It's a non-metal with a non-metal.
Non-metal plus a non-metal, exactly, right? So this is where it's important, where you guys got to know just what's a non-metal on your periodic table and what is a metal, right? So remember, group 1 and group 2 are what?
Those are metals.
Yeah, those are metals, right? And then all your transition metals are those little ones in the middle, the little from SC to ZN and down. Those are your transition metals. There's some metalloids, don't worry too much about those. But your non-metals are usually just your C and O, your gases, usually that you'll see when they form a compound, they're gases. So yeah, and then exactly, Jimena, thank you. I think it's you. Thank you for drawing that. That would tell you what your metals and your non-metals are, correct? All right, so let's say I made so let's say okay, let me do this. Okay, so real quick, what type of bond is this?
Covalent bond.
Covalent, right? So it's a non-metal. So you're telling me by that this is a non-metal and this is a non-metal. All right. So let's get into naming it. So for starters, well, what element is P?
Phosphorus.
Phosphorus, right? What element is oxygen? Oh, what element is oxygen? All right. Yeah, you guys should know that one already. It doesn't matter. All right. So let's just write it like this. So covalent bonding. Well, for starters, let's get one rule out of the way. All bonding requires what? All types of bonding will require one element to get changed. And what will that change be and which element? It doesn't matter if it's covalent or ionic. Just this is a set rule that we have to change always.
The second element?
The second element, and what about it are we going to change? The ending or the start?
The ending.
And the ending, so what am I going to change the ending to?
Ide.
Ide, right? So this, remember this, no matter what element, what type of bond, so ionic or covalent, just the second element, so the one on the right, the second one, will always get the IDE ending, oxide, D, okay? So, but now the covalent, so now that we got that out of the way, covalent tells us that we need to do some other stuff now. And what is that other stuff that I mean? Some other type of naming that we got to do to all these.
The Greek prefixes?
The Greek prefixes. So prefix is just before a word. So we got to tell you guys how many, we got to tell whoever we're telling that there's a certain amount. We got to tell them that there's 2 phosphorus and 5 oxygens. So Sebastian, you said Greek prefixes. So let's look at the second element. Does the second element for sure need its start changed?
Yes.
Yes, right? So what would you add on it?
Pent or penta.
Pent, yeah, pent, yeah. So you would put pent, I think. I think that's grammatically correct. So yeah, thank you. So this would be called, I'm gonna write it up here just because I'm running out of space. So this is pent. And so when you combine it with an O, you usually just leave it like this. But yeah, remember that it is penta, but this is just like grammar stuff. Like this is just like that you got to do pentoxide. Okay?
Only in covalent bonds is it when you name it like this one right here, it'll be like phosphorus pentaoxide. It's only in covalent bonds?
Yeah, it's only in covalent bonds where you use the start. Exactly. So we have phosphorus here. So do I need to change the ending of phosphorus?
No.
No, right? So yeah, remember, also for most bonds, you never change the ending of the first one. It just stays the same. So we do got to change the start. So we have 2. So you said di, right? Because that means 2 in the Greek thing.
Yes.
So yeah, this would be called diphosphorus pentoxide. All right, so that would be the correct naming for this. So let me give you guys one more examples because we're almost out of time. So what about this? Does anybody know what that's called? So it doesn't have a charge. It's not an ion, right? So it's a compound. So what type of compound is it?
Is it a covalent bond?
Covalent, yeah, because non-metal, non-metal, right? So we're going to use the Greek naming, correct? So let's write out our elements first. Don't even worry about the naming. So oxygen. So remember, no matter what type of bonding, what do we have to do to the second element? We have to add the IDE, right? I hope everybody knew and they were just shy. But yeah, it would be IDE. So do we change the ending of the first element? No, right? Because remember, you don't change the ending of the first one. So it is covalent though, non-metal, non-metal. That means we do have to use our Greek prefixes to state how many there are. So think of an imaginary one right here and an imaginary one right there. So let's start with the oxide. Do I have to tell you guys do I have to use a prefix for this?
Yes.
Yes.
Right?
So,
I'm sorry? So it would be mono. So just remember, but you're combining it with an O, so you don't do like this. This is just grammar stuff. You just do monoxide, not monooxide. You just call it monoxide. All right. So what about the carbon? Well, there is one. Do I have to tell you though? How many carbons? No, right? So that's why you usually see this gas. I'm sure you guys have heard of this gas, carbon monoxide. So if I were to call it monocarbon, so let's say I added this to the start. So in a sense, am I necessarily wrong with me saying that? If I were to call carbon monoxide monocarbon monoxide, am I wrong?
No.
No, I'm not wrong, but it's not the preferred way. It's not, you don't need to tell, if the first element just has one, you don't need to state it, okay? So that's what I mean, like monocarbon monoxide is not wrong, but it's not the main method we use. The main method is not that, so we don't use it, okay? So it would be called carbon monoxide. So just remember though, you always got to do, if there's one of the second element, you do have to state it. That's why we did this. If there's one of the first element, we don't have to use the mono. But if there was 2 here, then yeah, you would use dicarbon, if that even exists. But I'm just as an example, you know? All right, so that was exactly on time. So I think we could stop the recording, but if there's any peer leaders that want to stay for examples, just say that right now. So, I don't know who the host of the meeting is actually, but if anybody has any questions, sure, we're still.
I am. Don't worry, Andre. I'm the host. Just finished office hours.
Oh, awesome. So we're still here for questions. For those peer leaders that have to go, I guess. Yeah. You can, but yeah, I don't know who's gonna stay here for questions. I think I'll stay for a couple minutes. But do you guys have questions?
If you guys have questions, I can also stay.
Sorry, I'm ducking out. I haven't eaten like at all today.
Yeah.
So.
Go eat, please.
Go ahead, Gail.
Bye.
Yeah. So I'll be staying around. Don't worry. So.
And Luisa, yes, only ions have charges.